The first one is by Mercè Crosas. She's online from Barcelona, so I promised her the next meeting to see if we can go to Barcelona. Then we are sure we have her live next time. She has been at Harvard University as chief data science, and she was closely involved in the Dataverse tool, and she's one of the authors of the FAIR Principles. In the past 2 years, she has been the Secretary of Open Government for the Catalan government. Her presentation is about the future of open science.
Thank you. Should I get started? Yes. Thanks for the introduction, and yes, I'll be very, very happy if you have the next meeting in Barcelona. We would be happy to host you here in our beautiful city. And I'm sorry that today I cannot be in person there. I really apologize. It's always better to be in person. But I will start my presentation. And I just want to start with a few words to say that I will talk from the perspective of the various hats that I've been wearing over the years, working a lot, mostly around data analysis, data sharing, data management, open data. But from the perspective of a researcher initially, then from the perspective of a senior administrator at Harvard University, but as a data technologist, more as even a programmer, a data scientist, and a person specialized in data sharing and data management. And lately, like it was said in the presentation, more as a policymaker, and all this gives me these various perspectives and experiences that make me think of open science in a very broad way, and that's what I wanted to share today with you in this talk, to just make the effort that we should try to make the effort to go a little bit farther with open science, to think of the here in the context of the European Open Science Cloud, to think about where is science today and in what direction it's going, and how we can make open science a broader initiative enterprise that helps to improve science. So it doesn't focus only on the traditional way that we define openness, but it focuses in the way science is becoming today, which is more increasingly collaborative, increasingly automated, right? More efficient with AI and automation tools to speed up some of the process of the research discovery, of the scientific discovery. Also needs to be, and it is increasingly responsible towards data, right? How do we treat sensitive data? How do we treat ethical and legal issues around data? And at the same time, it has to be increasingly relevant to society. It needs to engage society and work together with society, right? So in my talk, I will talk about these 4 things, and each one of them will be by just based on a study or paper, some work that has been done. In some of them, I have been the author. So, but not in all of them. I'll start with the part of being more collaborative and towards co-creation. In this case, I will talk about a study that was released in August 2022. And in this study, I was not part of it. I was not one of the authors like the other ones that I will talk about. But I thought it was quite relevant after some time. As we all know, during the pandemic, of working together as fast as possible to find solutions, right, for COVID-19. The OECD, the Organization for Economic Cooperation and Development, made an analysis of a case studies and a study in itself about how did COVID-19 shape co-creation, and another one is about the case studies themselves, describing this 30 comparative international case studies. So let me summarize this work by the OECD. So first, one of the interesting things during that period is that it gave a test bed for collaboration practices, right? So OECD took that took that as an opportunity to analyze these 30 international co-creation initiatives. What did they have in common? Most of them had collaboration that helped with initiative from the bottom up. There was also, in most of them, involvement by governments. And it also they had to make use in most of these initiatives of global and national networks and existing programs and infrastructure. But what did we learn from it? Or what did the study say that they learned from this 30 initiative? Well, so even if you just remember the first one, I think that it's already a very important one that to leave this talk with. That if we want to collaborate, if we want to co-create, it's very important to share this common goal. So having a purpose, a well-defined purpose, makes that collaboration that stronger. It seems obvious, but we don't always frame all the collaborations with this strong common shared goal, right? So that's one of the first lessons learned, that was the driver. So we could use that in times of crisis, but we also can use that in normal times where we have challenges, and we just find that the strong driver will be to have a common goal. So then what else we will learn? So that the networks and infrastructure that already exist should be strengthened during normal times, so that we're prepared for challenges that that need accelerated scientific discovery. It also was found that there is still room for more collaboration between researchers, right, scientists, and those that produce the tools, the solutions, in order to accelerate innovation, right? So this should not also happen only on type of crisis, but in regular times. We also found that that in general, across organizations, there should be more support of digital tools, platforms for collaboration, data sharing, open challenges. Also, very important in this collaboration, it's key to leverage all the wide diversity of actors. So I'll talk more later about that, but it's not only about collaborations across researchers, but it's collaborations across multiple actors. The government involvement that can be useful especially when the government helps as a network builder, right? It helps put together research with industry in particular. And then the other very important lesson learned is that user engagement is also essential if we want to, an uptake on the new solutions or what comes out of research, what is the applied solutions and tools and products of research. So that's the part about collaboration and co-creation. Even though throughout my talk, collaboration will be an important part of it. Now I will focus more on the fact that science is increasingly automated and how open science needs to address that help or facilitate this automation of science. So this part of the talk comes from a study. For all these studies that I'm presenting, you'll see that there is the reference, and since I will share the slides, you could go and look into a lot more details about this study, but I'll try to make a summary of what we did for this consensus study that was organized by the National Academy of Sciences, Engineering, and Medicine from the US. So, and here there is a list. I'm not going to go into detail of everybody, but the list of all the contributors to that study, of the committee the scientific committee members, and the staff from the National Academy of Sciences. So, in to explain about this study about automated research workflow, first I will define what an automated research workflow is. So these workflows or research flows have been in existence or have been used in multiple fields, maybe more in some fields across biology, in medicine, but also in physics and many sciences and many others. But the more recently, there's been this uptake of automated research workflows, right? And in this case, what it means is that for any research process that is defined from going from the model to design an experiment or an observation or simulation to get the data, and from the data to do an analysis to learn about the model, right? So this loop becomes now more automated with the help of AI methods and tools, with machine learning, with the help of automation tools in the lab. This integration of computation, lab automation, and tools from AI in all these tasks, in all these steps in the research process, right? For not only for the analysis of data, but also for designing an experiment, designing an observation, right? So that's when we have that is when we talk about these automated research workflows. And why are they more in existence every time? It's because they help accelerate scientific discovery, scientific knowledge at the end. But they can be done, and the fact that it is automated and that they are in some way repeatable helps reproducibility. It helps a more rigorous steps in the research cycle. So some of the examples of these automated and advanced research workflows in action could be in material. Well, as I said, it was across disciplines, but this is just a few examples that are described in a lot more detail in the study if you want to read the entire report. But there is some examples in material science, where, for example, the time required for synthesis and testing of materials gets reduced with these automated research workflows from 9 months to 5 days. In particle physics, also allowing experiments to achieve a given sensitivity with half of the data, so need less data, but we still have rigorous, high-sensitive study. In drug discovery, something similar, right? Where with fewer experiments, we can get to higher percentage of finding active compounds. In astronomy, where the automation of how the telescope will target what observations we'll be doing also gives a faster way, or a more rigorous way, more reliable way to design the work, the scientific observations, right, and the telescope time, and even in digital humanities, there are examples also in social sciences. So that is also the use of AI, of some more automated workflows, in this case with text analysis, for example, help us to discovery faster, in some way faster and broader, or more being able to use more data than before. So, or at least not always necessarily more data, but more representative of what exists. So in order to have these automated research workflows, though, we need collaboration. Here, collaboration comes back from the first part of the talk, right? Here that we need this multidisciplinary team science that consists of having groups or having roles in many expertise. So this is not, it's almost not possible anymore to say that one single discipline or single person will be able to learn across all those expertise that are needed, right, for teams like that help accelerate the research life cycle with automated workflows. So we need methods to manage and integrate and interpret large amounts of data, right? We need expertise in modeling and simulation tools that can be executed in a scalable computing platforms. We need also methods and interfaces for the analysis, for the diffusion, for the exploration, the visualization of the results, right? And we need, as we discussed here in this session, also the technologies that will make all this process, all this automated research workflow, right, fair, so that it can be as transparent as possible, it can be repeatable, it can be reproducible easily. So what did the study recommendations for this work were? So first, that as we start designing more and more of these automated research workflows, these I8RW, so we need to think of the design principles that should facilitate openness, reproducibility, and transparency, right? Thinking about fair principles applied to the workflows. That also they incorporate principles of responsible AI, because now these workflows using AI, that they prioritize the reuse and sustainability, and that it's driven also by the research community, right? That these workflows, the creation, the design of these workflows are driven by each research community, because it knows what it needs. The research community knows what it needs for these workflows. The recommendation said that we need further progress in openness and sustainability of the infrastructure. So not only the workflows themselves, these workflow tools, right, but the infrastructure, the code, the data that are required as part of those workflows, right, of this research process. We also need the research funders, institutions, and professional societies support the education and training, so that new researchers, new professionals working on science understand the design and the use of these automated research workflows. And the same with increasing the culture and the incentive for this use of automated research workflows, and then have always in mind this preservation of privacy, of data privacy, because of the amount of data that are used within the research workflows. So that brings me to the next part of the talk about being responsible towards science. I mean, towards not science, of course, too, but towards data. So for this, I will talk briefly about another paper that I've been co-author, and that's already from a few years ago, but there's been the results of it, or the principles of the paper had been applied and reused in some ways in building platforms for data sharing. So here the idea is that, well, building this, what we call the data tax systems that defines various levels of openness for data, right? Based on the requirements for security, for access, for storage, and for sharing the data. So just briefly, what is a data tax system and what is a data tag? The data tax system is one that helps you store and share data in a manner that respects these legal commitments and ethical requirements or promises. And the data tag itself, each one of these levels, right, or labels that you would give to a data set, is a set of the security features and access requirements for the handling the files in the data set. So an example that we worked on for the data tags levels that we've been working on for also application to the platform like the Dataverse software repository, and it's been applied also to other platforms. So is that there are 6 levels, goes from blue to crimson, blue being completely open, green, you can imagine an access, but you need registration. You still consider the data are open, but you asking some information before downloading the data. In some case, you need to agree to some data use agreements, right, or to some license of the data. But it's still open in the sense, I mean, this is all depending how we define open, but still is not sensitive data. It still can be made available easily, but there are different levels of how you access it. And then we go into sensitive data where it needs to be stored in a more secure way, encrypted, and so on. The layers to access the data are going to be more difficult, right? And again, I'm giving that as an example of this orange, red, and crimson, all the way to fully restricted. Then it becomes very hard unless there is a very specific reason to access the data. But the point here is more that you could define maybe only 2 levels, or 3, or 4, or 5, or 6, but that you don't need to think only that sharing data is binary, that you either share or not share. I mean, share openly or not share, but that you can have these various levels because data have the different restrictions, ethical promises, and so, and based on that, you will accommodate your what label, what data tag you give to your data set. Furthermore, you could apply some privacy-preserving methods. In this case, the work that I had been involved was applying differential privacy to release the statistics about a data set in a way that the data set these statistics can be open. Differential privacy is defined as an algorithm that it adds a minimum amount of noise that when to make the data still useful, it still gives you statistically the same result or the same interpretation, but it has, with this noise, it adds this mathematical guarantee to have the privacy of any individual in the data set, any row of the data set. There's a lot to talk about that, but since this is a short talk, I'm just gonna go into the next part of my talk about the importance of for open science and for science, first of all, but open science as a way to support science needs to do the same, needs to be relevant to society. And this is the part that I have learned the most in my last the last part of my professional trajectory as a Secretary of Open Government in the Catalan government. And this article, there is a reference here, summarizes in part what describes what the vision of open government that our team had. So in this case, just briefly to say that what I the way that I think that this is relevant to open science, to the European Open Science Cloud, to in general to science, is that we need to look at beyond the scientific community and the research community, and think of that. Going back to this collaboration and co-creation, we need to think about involving industry, civil society, right, and government, in addition to the research and the science. So in this case, well, it also means that it is important to engage citizens, right, in either to citizen science, to sharing data for common goals, like I was saying in the beginning, right? This need of having common goals that the science help us solve, right? We also could think of applying these principles of open government, of transparency, participation, collaboration into open science, and that what we do also should help inform policymaking. We say more evidence-based policymaking, so that we make laws that have been experimented, that are based on evidence, and all that help us create a society that is more open, that works in collaboration for addressing societal problems. So as a summary, my talk, I'll go back to these 4 areas that I've talked about to you today, with the examples, with a description of some studies for each one of them. First, to be more increasingly collaborative, the open science should be ready to foster multidisciplinary collaboration, but also co-creation of multiple actors beyond research and beyond science. It also should facilitate this interoperation to allow for automated research workflows, like I discussed, the more advanced workflows that help accelerate discovery in a rigorous and controlled way, in a reproducible way, so following fair principles. And then also that we need to do that with responsibility towards the data. And I give you the examples of the data tags of various levels of openness, and also of privacy preserving methods like differential privacy. And finally, let's engage citizens, make that relevant, working with citizen government and industry, so towards this more open society. Thank you.
Thank you very much. I think we have time for a few questions. Someone in the room? In the audience? Because there was this morning quite some discussion about sensitivity and access to sensitive data. And I think what Mercè Crosas did is give us 4 directions how to proceed, but also tools on how to move forward. And this idea of data tags, I just wonder if that would be useful to apply to the sensitive data. So there are no more sensitive data in the room. Then we solve the question. No questions? Then, yes.
Hello, I'm Anders Conrad from Dijk in Denmark. Many thanks for an inspiring talk. I was wondering also along the line of data tags that Ron just mentioned, did you also, it comes close to a sort of data classification. Did you think of any tools to help researchers to define which tags to apply to different kinds of data, so they just don't automatically say we take the most restricted one?
Right. Yeah, very good question. We did work quite extensively on creating some tool that would help, that it was like a decision tree in some way that would help decide, classify the data, right, based on some questions that were asked to the researcher or to the data provider. And that knowing about your data and in the back end of this questionnaire in some way, right? It was a decision tree based on a questionnaire. Then there would be the legal requirements. The only thing is that right now I don't know that I can give you a specific tool. We tried to build one for US specific laws. There are a very large number of laws related to data privacy, but there are many. In the US, they vary across states, and so it was quite complex to be able to include all of them. We could do it based on some laws like HIPAA for patient data and FERPA for student data. Then I know there are some groups in the Netherlands that worked from dance, that worked on building a tool, a similar tool. To be honest, right now I don't know what is the state of that tool, how advanced it is already, but it's a tool for using the European laws. So I think that would be very interesting for IOSC to think of how to use this data tag tool that this team in the Netherlands were building. To help you classify the data set, even when you don't know about you just need to answer some questions about your data, and it will help you to classify the data set. And as you very well say, that way you don't just choose the fully restricted, right? Because the idea is to encourage openness.
Okay.
Yeah.
Yes, thank you very much. And I'm pretty sure we will follow up on these discussions as we have people also from DANT at the conference. One quick final question by Klaas.
Now I feel bad because she was before me in raising her hand, but Klaas Vierenga, je hand. Actually, I was thinking in the same direction of as Anders was about data classification, and I was wondering if you don't have perhaps too many categories. For data classification, you usually stick to 3 or maybe 4, because you also need to be able to explain it to users. So I was just curious what your thoughts are on that.
Yeah. I think there would be. I mean, if I added the reference to the paper. In the entire paper here was a very short summary. It does discuss that you could choose. So just to have 3 or 4. So the idea is that when you build a data tag system, it means that you don't have only it's open or you cannot share. You have more than that, but it doesn't have to have 6. We used 5 at Harvard, 5 levels. And that was adequate. We had thought about adding the 6th one. So I agree completely that some simplicity, I mean, with 3-4 cases or classification levels would be enough. But at the end, I think it should be driven also by what are the requirements within the scope of the system, the repository, or the data space that you are sharing the data. That sometimes it might require more than that. So it gave that flexibility.
Okay, thank you. Please, could you hold your question until the next presentation? Yes, because I want to move on to the second keynote by Dr. Martin Romacker. He's a data and information architect at Roche Pharma, research and early development. And one of his activities is on the implementation and assessment of the FAIR principles. His presentation is on FAIR architecture and shifting towards a data-centric approach. Please.
Yeah, so thank you very much. Can you hear me okay? just have to fix the mic. Yeah, I'm very pleased to be here and to talk about FAIR in action. So I'm a part of a larger pharmaceutical company, which is called Roche, which sits in Basel and has globally about 100,000 employees. I'm also a part of a broader network within the industry, of course, including our own company, but also other pharmas, to really implement FAIR. And what I would like to demonstrate today, also with the title FAIR in Action, from application-centric to data-centric, using FAIR architectures and resources, is FAIR really works. And FAIR really works at scale. But before I go into the presentations, I think there are 2 points that I would like to make. So first of all, I'm really very happy to see the large level of commitment of the European Commission to the FAIR principles, and also seeing how all the contributing countries in ESOX really make a sustainable investment into FAIR and really support this mission at a global scale. The other point, which is quite interesting, is that, and it's actually a very strange experience to me. So for the first time in my life, I'm going to a conference and I don't know anybody. And this is quite surprising because we are working on the same topic, right? You more possibly from a governmental perspective, we more from an industry perspective. So I checked some of the people who are here, who are sitting on the audience. The good news is, so the maximum distance between us on LinkedIn is maybe 2 or 3. So there seems to be, at least in the networks, some connection between us. So I would like to start a little bit high level with the business case for FAIR and data quality, and then I'm going to talk about the architecture approach that we have been taking at Roche, which we call the Roche Data Commons. Show to you, outline the capabilities that we have to build, so build our semantic product lines, and then I would like really to walk you through a very good success story that really show you the benefits of FAIR. But I think it's also very important to understand that these days, I think there's also a dilution of the understanding of FAIR. So everybody says that they are fair, but I think if you want to be fair, you really have also to look into a fair assessment of FAIR matrix. And then last but not least, of course, conclusions and acknowledgements. So this is a slide I've taken from a colleague from Neo4j, Rick van Bruggen, which I really like a lot. And this also reflects a little bit the situation that we're having in the pharma industry. I think everybody wants to go through the digital transformation, and there are huge trends around that we all share. I think the first one is data-driven drug discovery. So we want to be data-driven in our decision-making and maximize on the value of the data that we are having. The other point, also a very important topic in the pharma industry, is personalization, personalized healthcare. We have drugs that work on a patient and that don't work on another patient, and we want to find out why this is the case. So giving the right drug to the right person is very important. Then we also look into decision making. We want to really bring our data assets into ways how we make our decisions, make this available, and really provide the networks that we need. For example, in the finance industry, this is used also for fraud detection. So if some suspicious transactions are happening, massive data integration. We're looking more and more into these 360-degree views of customers, of patients, and last but not least, the megatrend: artificial intelligence, machine learning. So if you are in a for-profit company like me and you want to do something at this level, you always get budget. But what is really forgotten most of the time, and this is also why I think this ESOX project is so fantastic, is that whatever these megatrends want to do, they need highly connected, linked, fair, high-quality data at the core. Connected data is at the center. And if we don't make the investment here to provide this data infrastructure from, say, more the hardware part up to fair data management and stuff like this, all of these megatrends will have issues to fulfill or to deliver on their promises. And one of the core components, if you want to have this highly connected fair data, is you have to bring in some resources, and in particular data standards, which are based on terminologies, metadata, dataset models, and ontologies. A small side comment, while we're also talking here about fair plus Q, is that there's also a misbelief that fair data is automatically of high quality, and high quality data is automatically fair. A very good example is that currency of data is a data quality KPI that has nothing to do with fair. So we have to be very clear that fair plus Q is what we want to achieve. Another point is when you look into the true costs of data management, this is also a topic that is not being looked into very much, is that when we, for example, in the pharma industry, we produce a data asset, like, for example, we're running an essay, we're running a study, we have a lot of visible costs that are quite transparent, right? You have the FTEs that you need to create the data asset. You have to procure materials like samples, reagents, compounds, and all the infrastructure, the machines, the IT, and everything that you need. But there are a lot of invisible costs that emerge because we are poor on data management, because we are possibly not verifying our data enough. And there is a huge industry around data integration and data transformation. So this is globally a trillion business, and about 40% of the IT resources are eaten up by simple ETL processes, map and merge, searching and accessing, data cleansing, data curation, semantic integration. And this is all lost effort, if you wish. We could solve the problem, this is my dream, but it will never happen, is if every data consumer could backcharge the expenses of the additional work that you have to the data producer, they would eventually change their behavior. But this will very likely not work out. So now looking at the approach that we have been taking at Roche and the data commons. So this is really something which also pretty much is a kind of an information-centric or data-centric revolution, if you wish. So here you see a 5-level abstraction, where at the bottom you have the layer 1, which is the infrastructure, data infrastructure, physical hardware, cloud, whatever you want. Then at the layer 2, this is where the data management happens. So this is where you manage your data assets, also with data workflow languages. We're using tools, and you are then providing then an access layer to this data that you manage at layer 2. Layer 3, and this is now the important point, something that we have called the harmonized data access points. Here, we have a completely information-centric organization of our data assets that completely abstracts away from application. You see some examples here to the left. For example, we group data around adverse events, clinical study, flow cytometry, medicinal history, informed consent, study, variant, all the various domains and subdomains we are having. At layer 4, this is where we then take this harmonized data access points and we are building integrated data sets. And last but not least, at layer 5, we are running the analytics, or we are providing tools. So at the end of the day, you're building applications on top of your data. And today is that you have applications and you try to get the data out of your application. So this is really flipping the coin from application-centric, where everybody runs applications, where you want to access the data, into information-centric, where applications are sitting on top of your information layers. And last but not least, applications go away, data stays. And all of this is held together, and you see it with the green bar on the left side, by reference data services. Again, the before-mentioned terminologies, metadata, dataset models, and ontologies. So how does this play into FAIR? And so when you are in a FAIR world, you have to be acquired that everything that you have in your universe is a resource. A file sitting on a file server is a resource. A set of files that forms a data set is a resource. A metadata tag that is used to describe a file is a resource. A code list is a resource. A code list element is a resource. And we all have to give these URIs, or now we call them GUPRIs, global unique persistent resolvable identifiers, to these resources. An ideal status is when you think, for example, about any kind of journal publication that you have. You have this DOI, this document, a digital object identifier, and this unambiguously identifies a publication across the globe, wherever you are, wherever you sit, at what time ever. And I think we want to achieve similar things with the data that we're having, but this requires a lot of governance on convergence. So data verification happens exclusively at layer 2 and 3. And then at layer 4 and 5, you only use your resources to dereference. So if you still have a lot of ETL, map and merge, data transformation between layer 3 and 4, there's something wrong with your verification. And again, this kind of verification really requires a lot of communication, a lot of prospective alignment across teams. But how do we know how fair our data, how fair our environment is? And I also would like to emphasize that, at least for us, fair does not only apply to data, it also applies to applications, and it also applies to services. There are many, many systems that cannot, for example, cope with global unique persistent resolvable identifiers. You cannot even read in a terminology, you cannot read in a schema which is semantically harmonized, and so on. So we have to look into fairness at 3 levels: data, applications, and services. And I mean, at the end of the day, this is also possibly where we converge with our ideas. We want to have an open public-private semantic infrastructure of fair data, services, and applications. So I have a little bit of kind of a human readable interpretation also of FAIR, which is from my colleague Olivier, who's also working in the same organization. And he looks into 2 different aspects about FAIR. One is the human aspect, and the second one is the machine aspect. So human means, for example, in our world, that a scientist or a data consumer is able to find, access, and understand data without the presence of the data owner. So data are really easy to find, access, and also have all the semantic explanations that they need to be able to be used. The second part is possibly more important. It's the ability of a machine to automatically find and semantically use the data. And there's, we'll come back to this also, a difference between machine readable and machine actionable. Because machine readable only means that you're able to read in something in electronic form, but you cannot immediately act on the data. You still have to do something, enrichment, curation, or verification, whatsoever. So, as mentioned before, we are part also of a community. Here I'm referring, for example, to a project from the so-called Pistoia Alliance. That's a non-for-profit organization to foster collaboration between companies in life science R&D. And we also provide resources to work with. And here we have a FAIR toolkit, where we also provide the FAIR maturity indicators. And here's a screenshot from this Pistoia Alliance project. This is the FAIR metrics with the maturity indicators. But I think what's very important is that also the FAIR maturity indicators stress the importance of these identifiers. If your workflows are purely string-based, you use names, then you are not fair. And at the same time, this is more the strict reading also about interoperability, is that you're ideally supposed to use terminologies and ontologies, which are, again, machine-readable and fair. So the input and the verification are fair resources. And last but not least, I think this is quite obvious, FAIR is about data and metadata, so the way how we describe our data. So what do we have internally at Roche? Just have a high-level summary slide on the product line that we have to support verification at scale. So we have a so-called scientific interoperability hub that possibly doesn't come too much as a surprise from the slides that you have seen before, has 3 different products. One is we have a decent terminology management system that we have in active use in more than 100 applications at Roche, and this resource itself is fully fair. We have a place where we have a metadata registry where we can also define semantic data sets, and last but not least, we can also do conceptual modeling, which we call it purpose-driven ontologies. The products are fair by design themselves, and they support verification at the entire Roche organization, and it really ensures semantic interoperability and high quality of the data. These products also serve as reference data for standardized terminologies, the metadata and the conceptual models, and we really link semantically the internal knowledge space, but also the external knowledge space, which helps us for data acquisition, data generation, but also data integration. And a very, very important element of our service is that we don't provide a technology and say, okay, this is out here, so please use it. We also trace the way to the people, so we have to the usage, sorry. So we really have a service that helps to bring people on board of this platform and making their data really fair at the source. So this is how the stack looks like a little bit more, in a picture. So at the bottom you have, these are also screenshots from our terminology management system, which is an in-house development using standards like SCOS, if you know them, or Dublin Core, or RDFS. At the middle we have the dataset models, the metadata registry, and then we also have here the conceptual models, which are the ontologies. What's really quite nice, if you follow the path of verification from the bottom to the top, what you get when you want to integrate data is a unified model that comes with almost no integration costs. So we have, and this is the example I'm going to show in a second, we have completely transformation-less data workflows. And this is another example from the work that we have been doing. We had a 5 years program at the organization, which is what calls EDIS, Enhanced Data and Insight Sharing. And here you have a data management plan from planning, acquisition, processing, release, and access for studies, for clinical studies. They've just marked up symbolically the places where we have verified everything. So the verification is a part of the process. It is prospective. It doesn't happen retrospectively. On the next slide, you see a similar view where we take again the Roche data commons. On the left side, you have our systems here, and some of the elements we have at the different layers. So here we have our Roche corporate net infrastructure, the various data management systems, data catalogs, the harmonized data access points. So they have all been verified prospectively. They're all using URIs for indications, for drugs, for companies, whatever you want. And then these are the quarters here. The blue quarters is we are building then applications on top of this integration. And this is what I want to show you in the last example, the Roche dataset portal. Just checking how I'm doing in terms of time. Well, still doesn't look too bad. Okay. So we have a dataset portal at Roche, which is a data catalog of data catalogs. Because it will be extremely difficult to have one data catalog in a huge organization like ours. So a data catalog ideally should be a federated object. And in this data catalog, we have data from many, many different data domains. We have biomarker data, we have clinical data, we have digital biomarker data, imaging from various areas, omics, so this is proteomics, transcriptomics, and genomics, real-world data, all different kinds of data. And these data are being cataloged and published into a single space that also has an internal search page, and then it can be searched in one place, so a one-stop shop from the scientists. This is how the user interface looks like. So on the left side, you see some of the data providers that feed data into this dataset portal. And on the right side, you also see that you can use the semantic descriptions that you have for your data in a user interface, for example, for facets. So you have on the top left here, just taking the laser, you see these are the data providers with the number of data assets that they have published. Then you have facets around the drug that has been used, the phase, if you have some studies, or indications. And this is all model-driven. But how do the things play together? So we have built a semantic model for the R&D dataset portal that is completely following the FAIR principles. And the FAIR principles also say, use community standards whenever you can. Don't create your own resources if you don't have to. And for data cataloging, there's a nice standard which is called DCAT that you can see here on the bottom. Then if you want to have more information, there's also something like provenance ontology that you can use. But the amazing thing here is that this model has been produced without defining a single proprietary property or class. We're just using everything from the community following the FAIR principles. And all of the elements which are in the model, on the left side you see here, this is a Vidoco document that you can generate out of your model. You see, for example, you're talking about contributors, you're talking about departments. All of these are resources that can be dereferenced. I can get information about pharma informatics here, or on the right side, information about a specific contributor to the project. And last but not least, also, if you want to describe your data in the data catalog, the various terminologies, the terminology elements, it's all FAIR, all coming out of our reference repositories. And the key point now of bringing all these elements together is that we are having so-called data contracts. So in the middle, you see the R&D dataset portal that has these many, it's just half of them, feeders that have their own data catalogs. And there's a contract how this data is going to be procured to the consumer based on the FAIR model that you have seen before. So our take is that connectors are out. So connector is an active act from an application that wants to consume something to go to the provider of the data. It is more the inverse. And this also plays into the new upcoming notion of data products. A data product owner wants to open up the system, make it available, and increase the usage of the data. This is why all these systems now open up their content and they provide a standardized interface for which we are using JSON LD. I don't know how many techies we have here. Techies, please raise your hands. At least there are some, yeah. So JSON-LD is a specific dialect. LD stands for linked data that is perfectly suited to support fair at scale. We also call them smart APIs. And we have used now JSON-LD APIs. And for the next slide, I have to ask for forgiveness because it's a little bit technical. But what I want to say, this is just the JSON-LD that you see here. So in JSON-LD, there are two important points. One is that you get the full semantics of the information that you ship in a so-called context file. So everything that you see here, for example, at the top, we're using, for example, a property which is called in scheme. In scheme is a SCOS standard property, so we're using terminologies, and all of these semantics for all of these elements, they are in the context file. So you can not only read the file, it is actionable because you get the full semantics. And then we spec out all of the other information, again, with these global unique persistent resolvable identifiers. Here, for example, it also plays into the previous presentation. We have our own URIs to indicate the level of sharing. So the license here is red. That means it's not for public sharing. We also have then URIs for our study identifiers. We have URIs on the left that you can see here, if you can see it. Otherwise, go to the slides, please. About all the metadata, what is the indication, what is the study name, and then we follow the DCAT standard where we define a dataset version, a distribution. This is really something that you can use. And the result of this is read into the dataset portal without any transformation. Just call the JSON-LD endpoint and it's there. And because we are having this, and because our data are machine actionable, we can also perform automated fair assessment in our dataset portal, where we evaluate the message that we receive against the model that we have for the R&D dataset model and the values that are in there. And again, sometimes people are surprised because they get a lower fair score, but please be aware, make very, very clear, this is not to police people, it's really to support them, okay, where are you in your journey towards fair, and how can we support you to improve you? So, conclusions. So if you want to be successful and you really want to generate value with digitalization and provide true, you have to provide true machine-readable, machine-actionable data. Machine-readable is not sufficient. And in this case, the application of the FAIR principles is mandatory. And now comes the next implication. If you want to apply FAIR data principles, you are intrinsically in the space of semantic technologies, where you define FAIR terminologies, FAIR metadata, FAIR data sets, and also FAIR ontologies. Transformation-less data integration based on full harmonization and data sets is possible, but it really requires a fully linked data ecosystem and that you can produce more reliable insights in less time at lower cost. So prospective verification is the key here. And if you want to have this data mastery, also a term which is quite used there, so really master your data management value chain from the beginning to the end, production until analytics, you really have to go new architectural approaches around data information, and the scientific interoperability or the semantic interoperability of terminologies, data set definitions, and ontologies is key to make our data sets machine readable. So at the end of the day, everything is about semantics, not only about infrastructure, about the meaning of what you want to convey. I'd like to acknowledge my colleagues, and thanks for your attention. I'm happy to take questions.
Thank you very much. Can we start with your question?
Now I have to rework my question because it was a question to Mercè, and in a way what you proposed, Martin, was not really answering it, but the question remains, and that is, do we actually make researchers aware enough that there's a difference between the data itself and the metadata, which brings the semantics? And you've shown in your case that this metadata is the key. And the question is whether in our training activities and when we try to persuade decision makers at research performing organizations, do they really get that difference?
I think this really touches the key point of the entire story. And I think there are, to answer to your question, I think we do not make them aware enough. That's one point. The second point, I think also that was mentioned before, is I think we also have an opportunity with the architectural approaches to make systems fair by design. So then when data are created, they are born fair. So in essence, it means that you have some structured data entry forms, and you're not allowed to create a new value. It's all governed. But I think in terms of communication and really bringing this to a broader scale, I think we could certainly do better and more. And I think this also applies to the researchers that we have in our commercial organizations. Communication is really key. And the other point is that when you talk to researchers, you get this typical feedback, I have to have my freedom, it takes so much time, I cannot do it, There are all these kind of excuses, but they are at the beginning of the data management value chain, and they are possibly the most important people that should also, by the way, then be incentivized when they do a good job.
Yes, thanks, Volker Beckmann, EOS Steering Board. Thanks for the very inspiring talk, where we see EOSC as the overarching organization for public research. We see Gaia-X for the private sector. As far as I understand, Roche is not part of the ISBL. And can you comment on the interest in joining an organization like Gaia-X for a company like yours?
Absolutely. I think there is overall a strong interest. The only concern that I have to express is that I think it's for someone who works in the industry, it is quite difficult to keep pace with all the initiatives that are popping up everywhere. I think there is a huge universe of, governmental-driven approaches, also sometimes in Europe, sometimes in the US. You also may know that we have a dedicated program in the EU IMI, Innovative Medicines Initiative. So at the end of the day, there is a high interest, but I think it's also a question where we can allocate our resources, because we also have to deliver on some stuff. But I would guess that I remember that this Gaia-X was mentioned several times internally, and if you want, I can also follow up on this.
I think this is for the coffee. I want to go to the final question. Giorgio?
Yes. So I take one important message from your presentation, and that is that even in a sectorial domain, like life sciences at large, but then pharmaceutics, FAIR is the good solution, which is a good message for the data spaces that are being created and supported in different domains. And that is the first point. Second point is that EOSC is trying to do an overarching system of FAIR data, covering all the scientific data issuing from different communities, different domains, in the perspective that combining information from very different sources might generate new knowledge. Now, from the point of view of Roche, of a pharmaceutical or whatever company, having access to FAIR data on population, migrations, climate change is a strategic asset for you, or you think you will stick mostly in the sectorial data space?
I possibly have to say it's more my personal impression and opinion, so I'm not officially speaking for Roche, but I would say there's a huge interest to collaborate more, and it's not only about taking, it would also be about giving. I'm currently working with some colleagues in the Netherlands who are working on FAIR implementation points, where also, for example, Roche would expose clinical data via a FAIR implementation point to a broader community. So I think what is very important really is that we see this as a community effort. And of course, there's a part of what we have as data that should be private because of IP. But I would definitely feel across the entire industry a change in the mindset towards being more open. If you want to be more open, we also need to align on architectures, on approaches. And I think, as you said, with your first comment, FAIR is the right way to go.
Okay, thank you very much. I think we could have more questions and discussion, but let's have that at the coffee, which starts now and finalizes at 4. Sarah?
Yeah, I can give you 5 extra minutes.
She's very generous today, so it's 4:05. We will be back.
Yes.
Thank you, Martin. Thank you, Mercè.